Now we have a charged plane, and it extends to infinity in every direction. And suppose we have the charge density sigma, and it is uniform, it is a constant over all the plane, and we are interested in finding the electric field at a point which is a distance, perpendicular distance d, away from the surface of the plane. So again, we will choose a Gaussian surface, and this time, since the symmetry has planar symmetry, we will choose the planar Gaussian surface. In fact, we will choose a pillbox which has a finite volume. So this pillbox is a rectangular region of space, and it cuts through the planar charge distribution, and it extends to the other side. And since we want this region symmetric around the charge distribution, so we should take also the down region as our part of the Gaussian surface. So this is the Gaussian surface, and the next thing is we will calculate the flux through the surface, and we will be able to express this flux in terms of this electric field at the point in question. And we will use some symmetry arguments, of course. And symmetry argument says that since the planar charge is a positive charge, then it is very obvious, very intuitive that the electric field will be in the direction which is perpendicular to the surface of the charge distribution, because the electric field is always pointing outward from a positive charge. That means that will make much of the things easier in calculating the flux through this rectangular region, because choosing a point on this top surface of the Gaussian pillbox at anywhere will not make any difference in the strength of the electric field, because wherever you go on this top surface of the Gaussian pillbox, it will have a same distance to the charge distribution. So wherever you go, you will see exactly the same charge distribution. Since there are no edges of the plane, it is an infinite plane. Wherever you go on this parallel surface of the top of the Gaussian pillbox, you will see exactly the same charge distribution. That means at any point on this top surface, the electric field will be the same. So this is our symmetry argument. But on the other side, at the down region, again, any point on the bottom surface will see the same charge distribution, and the electric field will be pointing downward, of course. So we will come to this point in short. Alright, so on the top, the electric field is away from the surface upward, and on the down, the electric field is in the downward direction. Alright, so maybe it is better to picture this distribution from a side view, and the cross section will just look like this. We have this charge distribution, and this line represents the plane, and the plane is perpendicular to the surface of the board, and this is our rectangular pillbox. Okay, so the electric field is up in the upper region, and it is down in the down region. So what about the area vectors of these pillbox? The top surface, of course, since the area vectors will always be perpendicular to the Gaussian surface, closed surface, the top surface will have the area vectors which is in the upward direction, which is parallel to the electric field. And in the side surfaces, since the area vector is always be perpendicular to the surface, it will be in this direction, for example, onto the right surface, and in the left surface, the area vector will be pointing in this direction to the left. So on the down surface, of course, bottom surface, the area vector is again parallel to the electric field in that region. Okay. So let's label the fluxes through these surfaces. Let's label the top surface, the flux of the top surface phi 1, and the flux through the bottom surface as phi 2, the flux through the side surfaces phi 3 and phi 4. Well, since we have 6 surfaces, I just didn't show you the rest of the surfaces because they will be parallel to the surface of the board. Anyway, because of the directions, you can easily realize that the flux through the surface, the side surfaces, will be equal to 0, because the on these surfaces the electric field and the area vector are all perpendicular to each other. So the dot product of them is equal to 0. But on the bottom and top surfaces, since the area vector and the electric field vectors are in the same direction and they're all constant through the top and bottom surfaces, it will just be the electric field times the area of the top or bottom surface. So let's call A as the area of the top or the bottom surface, because since it's a rectangular region, a rectangular box, these surfaces will be equal to each other, and let's call one of them as A. So the total flux, of course, will be the sum of all fluxes, and this is phi 1 plus phi 2, and it is 2 times the electric field strength E times the area of the one of the top or bottom surfaces. Well, from now on we will apply the Gauss's law. The Gauss's law says the flux through any closed region of space is equal to the charge which is located in that region divided by epsilon 0. So the question in here, what is the charge inside this rectangular box, the Gaussian pillbox? Well, it's very easy, because the cross section with the rectangular box and the planar surface is just this square, or whatever you call it, because it may be a rectangular surface or a square surface in here. Well, this area again, as you see, since this is a rectangular surface, it will be the same area A with that of top or bottom surface. So the question is, what is the total charge of this region, because this is located inside the rectangular box. And it's very easy, because since we are given the charge density, surface charge density, to find the total charge is just multiply the surface charge density with the area, right? So Q in is nothing but the sigma times A. And the next thing is we equate these two quantities. On the left hand side we have the total flux, on the right hand side we have the total charge divided by epsilon 0. So from this equation it is very easy to get an expression for the strength of the electric field, because we cancel out on both sides the A's are the areas, and we reach the result. The strength of the electric field is equal to sigma divided by 2 epsilon 0. So the strength of the electric field, as you see, does not depend on the distance of the point from the surface. It's very interesting. It does not depend on the distance. Well, it seems a counterintuitive argument, because well, you will think that when you come close to the surface or charge, the electric field strength will be large. But imagine if you are yourself on this point, and if the plane extends to infinity. So wherever you look, whichever direction you look, you will see exactly the same charge distribution, whether you are close to the surface or not. you will see exactly the same charge distribution. So because of that, you might maybe understanding or realizing that the electric field strength will not depend on the distance. Alright. So the immediate consequence of this is, let's imagine we have two planar surfaces, okay, just like we had in the example. One is having a positive surface charge density, and parallel to it we have another parallel plane which is large again, but this time it has a negative charge density. So we have two planes, one is plus and the other has minus surface charge density. But the question is, okay, they have the same strength of the surface charge density. Okay, so this is the example. Alright, so to calculate, the question is, what is the electric field in between these two planes? Okay, or let's say in every point, every region. So we have three regions. We have top of the plus surface charge density, we have the region in between these two planar surfaces, and we have the region which is down to the minus surface charge density. Let's write down the electric fields around the total electric field on these three regions. If you think the top region of the plus surface charge density, we have, let's label this E plus, the electric field, and because of the same surface charge density, plus surface charge density, the region in between will have a downward electric field produced by the positive surface charge density. And since downward in everywhere, because of the plus surface charge density, the electric field will be in the same direction. It is the same electric field and it's the same strength, because again we are imagining that these surfaces are very large, and the electric field strength does not depend on the distance. So let's do the same for the negative surface charge density, because at the end we will superpose the electric fields. For this region, the electric field, because of the negative surface charge density, will be downward, and in between, again it is downward, because it still we are on the top region, and at the down region, at the very bottom region, the electric field, because of the surface charge density, will be in the upper direction. So if you superpose these electric fields at every three region, then you will see that the top region of the plus surface charge density will have two electric fields, but they are opposite to each other. So they will cancel each other, because the strength of the electric field is the same, but they are in opposite direction. And it is the same for the very bottom region. The electric fields are in the opposite directions in here, but in between, the electric fields produced by both planes are in the same direction. If you add them, you will have 2 times the sigma divided by 2 epsilon 0 will give you sigma divided by epsilon 0 as the electric field strength between two planes which are oppositely charged of same strength. Okay, so this is an immediate application of the planar charge distribution, planar symmetry of Gaussian law for calculating the electric field between two oppositely charged planes.